Hello everyone, welcome to my channel. Today I want to talk about C++ atomic operations, and I want to talk about the memory orders of atomic operations. Uh, Atomic operations is very important for synchronization in threads where we don't have to go through the system level of locking, having a memory fence, and so on. So it's if you have two threads that is depends on each other, but the timing of dependencies is very small. You don't have to. It's not a long time waiting. It's more efficient using atomic operators. So this so atomic operators, it was initialized by STD atomic, and but there's many cases how compilers and CPUs can optimize your code so that it runs more efficient. And it all depends on how your code was written. What is the logic behind that? So there's multiple memory orderings and functions that comes with atomic operator that programmers can use to further optimize the execution of the program. So the first one I want to talk about is the STD memory order sequence consistent order, which is the strictest memory order. And then we're gonna talk about acquire and release or memory order. Then we're gonna talk, so that's less stricter than sequence consistent. And then we're gonna talk about another further less constraint, which is consume and order release. And last, we're gonna talk about the most relaxed constraint, which is the memory order relaxed. So we're gonna talk about those different memory orders. We're gonna see how what are the differences when we should use which order, which memory order. So maybe we can first talk about the first two, which is first is the most relaxed, and then the most strictest, which is order sequence consistent. So what is order sequence consistent? So let's look at this example here. We have four threads. We have a write. We have four atomic operators here. Four atomic variables, uh, x, y, and z, and and we have four threads. The first thread is writing x, so x becomes true, and second thread is writing y to become true, and third thread is read x and then uh, and then y. Last thread is read y first and then read x. So the memory order consistent has three properties. Uh, if we are storing a value to atomic using order sequence consistent, then it behaves to so that the memory is so that all the operations uh, above the store are visible to other threads. So that means that uh, so the memories the memory operations above the line 135 cannot be moved below the line 135, and it becomes visible to other threads. What I mean visible to other threads means that if at time t we run this line, then all the changes on above this line, all the memory writes and reads, all the memory modifications will become visible to other threads. And if we are trying to read something, uh, then the reads will have another fence. So any use of x will not be moved above the read. So basically means that the code, how you write the code, the CPU we're gonna run that sequence. So that's it won't reorder the memories or running two uh, lines of codes in a different order. So we'll be always following your code's order. So that's one of the properties. The second very important property is consistent timeline. So there's only one single timeline. So if the CPU runs this line, so this line's change to X will be visible to other threads, and all the threads they agree on the same timeline. There will be no thread A has its own timeline, thread B has its another timeline. So if at time t X is changed, at time t plus 1 Y is changed, then other threads will also agree that at time t X has becomes true, and at t plus 1 Y becomes true. So the read X then Y and read Y then X, they won't see a different timeline. So it won't happen, for example, read X then Y will see X becomes true, but Y is not. Or read Y sees Y becomes true, but X is not. So there's only one single timeline. Everyone will see the same timeline. Okay, what instruction has been changed? What instruction has been executed? So this is the strictest. So it is exactly as there's only one CPU, and every thread is running at one CPU, and the one CPU has its own timeline. Everyone agrees on that single timeline. And so before the CPU becomes multi-core, this is exactly what is happening on programs. But since we have multiple cores and there's multiple layer of caches in different CPU cores, then the memory may not be synchronized on different cores. So that means that every core has its own timeline, which means that they see different things on memory. But memory order consistent, sequence consistent means that okay, every CPU core, we agree on one single timeline. If someone changed that on the early time, then everyone sees that. So that's what it means. So if you look at this example, if we run this fourth thread, the first two threads is writing X and writing Y. The third thread is first read X and wait until X becomes true, and then we then read Y. If Y is true, we do a Z plus Z. And fourth thread is the reverse order. We're gonna wait Y to become true, and then if X is true, we do plus Z. So if we are now using order sequence consistent memory order, then these two threads, thread 30, read X then Y and read Y then X, may see two different timelines. So read X then Y may see X is true, but Y is now true, and read Y then X may see Y is true, but X is now true. So in that case, none of the Z plus Z will be run. But if we use memory order consistent, then if the two threads write X and write Y, they run on the CPU on two different timelines, on two different times, T and T plus 1. And this sequence will be, this order of execution will be agreed on, will be seen by these two threads, and they agree on the same order. So they won't see different orders. So that will make sure that the changes will be consistent, and that's what they see is consistent, and basically it means that every code we run, so it's memory order, no memory reordering, and timeline consistent, single timeline they agree on every thread, they agree on what is run on a certain time. So that's the memory order memory consistent, and because of that, Z will never be equal to 0, because if which means that it won't happen that read x then y, since x is true, y is false, and then read y then x, we see y is true, x is false. It won't happen, because if x is true, then if x is true, then read x then y will finish waiting, and then if y is false at this time, then this one plus plus. But then if y is set to true, read y then x will exit from waiting, and then x will always be true, because this thread will already see x is becomes true, and this what he sees would be also be the same as what the other thread sees. So x will also be true, and z will always be +1. So this will never be 0. So that's the strictest memory order. Let's look at the most relaxed memory order. So the most relaxed is using memory order relaxed, and which means that it doesn't care of the memory above it and memory below it. So what it means that if and it only cares about itself. So y will be guaranteed it will be run atomically. So or the let's say fetch and add, that's read and modify. So that will be that operation will always be atomic. Other than that, there's no guarantee of other things. So what we will see if we use memory order relaxed, we could see multiple different behaviors. So if we line these two threads, T1 and T2, we line the bodies as A, B, and C, and D. Then we might see C and D was run before A and B, and that in that case, we're gonna see R1 is 42 because Y is set to 42 first, and R2 is 0 because AB is run later. And we could also see that we run AB first and then CD. And in that case, R1 is 0, R2 is 42. And also, we could also see, this is very important, this part is very important, we could also see D was run first, A, and then A, B, and C. Why? Because that's what I just mentioned. The order doesn't matter. So because this line, even though it's after the line C, but this line has no dependencies on the X or R2. So this line, the compiler may reorder, because these two lines are independent. So either the compiler or the CPU could run these two lines in a different order. So D could be run first and then C, or they can run at the same time on two different CPU cores. And in that case, we might see R1, because these run first, we might see R1 is 42, and then because C is run last, we also see R2 is 42. So we might see different behaviors when using memory order relaxed. But this is very efficient, especially in shared pointers. So this is also very important atomic operation memory order. So next, a little bit stricter memory order than memory order relaxed is the consume and release memory order. So memory order consume and memory order release. So these two, what are difference? So first thing is, if atomic store in thread in a thread is in thread A is tagged with memory release, in thread produce is tagged with memory release, an atomic load in consumer is from different variable that with the store value is tagged with memory order consume. All memory writes, including non-atomic and relaxed atomic, that happens before the atomic store, uh, will become visible side effects within those operations in thread B, into which the load operation carries dependencies, which means that uh, only the dependencies, which is the atomic pointer, this atomic PTR changes, will become visible effect to the other thread, the consume thread. And the changes that is not dependent on P, on the P that P pointer is not depends on, will not be always visible to the other thread. For example, the data, which is now related to pointer that set it to 42, may now be visible to the other thread, which is consumer. So we may now see consumer after we the pointer low becomes null. We exit from the waiting. The data may not be 42, but we are sure that the pointer p, which is dependent variable for PTR, will be seen. We also see pointer PTR itself, the atomic operator, will also be seen, will always be true, equals to hello. But there's no guarantee that data will be seen. So the data variable, which is independent of P pointer atomic, will not be guaranteed to be seen. So that's a little bit less relaxed. It's not fully relaxed, but it's less relaxed. And then we go another little bit stricter, which will be a little bit different than consumer release. And the new one will be the acquire and release, memory order acquire and memory order release. So this is just a little bit stronger than memory order consume and memory order release. What this guarantees is that all the memories changes before the store will be seen, all the memory changes before the store in producer will be seen by the consumer when it loads. So the data change that we are not guaranteed to see in the consumer, data change to 42, we are not guaranteed to see in the consumer, will guarantee this to be seen by the order acquire and release model. And that's the difference. So it becomes even stronger. So even though the instruction that data is being set to 42 is now it's not a dependency to the atomic pointer PTR, because it's before the PTR is being written to, so it will be seen by the consumer after it loads the PTR. So that's the acquire release. And let's see another example of acquire release, which is very often used as alternative to the conditional variables and mutex, which is the memory order acquire release, which is a combination of acquire and release on an atomic variable. In our case, which is atomic variable called flag. And what this does is we are using this flags compare exchange weak. There's also a compare exchange strong. The difference is very tiny, but it's not the topic here. So we're gonna just look at the weak, use the weak here. So compare exchange is operation that that if the flag so it compares the contents of the flag with the expected. If it's true, if these two are equal, bitwise, it's a bitwise comparison. So if these two are equal, it replaces the flag with the desired value 2. So the second value will be set to flag. If it's false, so these two is not equal, then it will replace the flag with it will replace the expected with the flag. So the flag value will be set to expected. So and those operations are, as you can see, are read, modify, and write, or it's a load operation. So in that case, we want to use the order acquire, really release, because we want to make sure when we read, we are doing a memory order acquire, and when we write, we are doing a memory order release. So that's another example of acquire and release, and the sequence consistent we just mentioned, and that's what I want to talk about today. Hope you like it. Bye, everyone.